Okay, this is chapter 2. We're dealing with a number of different things. Continuation of chapter, or excuse me, not chapter 2, chapter 3. Continuation of chapter 2 with inclined planes, pulleys, centripetal acceleration. We'll deal with some friction, largely inclined planes, and we'll see some pulleys, other simple machines. So the following system includes a frictionless pulley and a cord of negligible mass. Since the system is at rest, what can be said about the force of friction between the platform and the large weight? Well, I have forces acting on both of these. I have a tension here. I have a tension here. I know that these two tensions have to be the same. I have the weight here, and I have the frictional force Fs. Now, this is stationary, it's not moving, so these two forces have to be equal. The tension equals the weight, so tension equals 10 newtons. And this tension right here is the same as that tension. So I have 10 newtons there, and since it is stationary, Fs, which is what it's asking about, has to be 10 newtons. So B is the right answer. An object with mass m sits on a plane inclined from the horizontal at an angle theta. Which of the following represents the normal force on the object due to the inclined plane? All right, notice these are all given in the angle theta. You should become very familiar with expressing these various things: the normal force, the acceleration down the inclined plane, the frictional force, in terms of this angle theta. I can draw my vectors here. I have a weight, Fw, and then I have the normal force acting in that direction. Let us draw a coordinate system, and then recognize that this angle is equal to theta. Okay, so here I'm looking for the normal force. The normal force is going to equal the y component of the weight, and so the normal force will equal the weight times the cosine of theta. It's cosine for the y component because this angle theta is measured from the y-axis. So you really need to be familiar with these terms. What is the acceleration down the inclined plane? What is the weight? What is the normal force? And how to use these. So the answer for number 181 then will be B, mg cosine theta. An object with mass m is placed on a frictionless plane inclined from the horizontal at an angle theta. Again, the same scenario. Which of the following represents the acceleration of the object down the inclined plane? Well, my force down the inclined plane is going to be a component of my weight. So this is my weight. This is the angle theta. That is the x component of the weight. And so this force, which is down the inclined plane, is going to equal Fw sine of theta. All right, but here I'm not looking for the force, I'm looking for the acceleration. So I'll just divide both sides by m, and I will get g sine theta, that is A. That gives me the acceleration down the inclined plane. Again, really something you just need to be very familiar with and just be able to produce at any point. For the frictionless inclined plane below, h is the height of the ramp, d is the total length of the ramp, and theta is the angle the ramp is placed from the horizontal. And x is also frictionless. If h is 5 meters, m is 2 kilograms, and theta is 30 degrees, and the mass starts from rest, how long does it take the mass to move the distance d? I already know that the acceleration is g cosine of theta. So that's going to be 10, what was theta here? Cosine of 30. So I'm accelerating this length d by 10 cosine of 30. The cosine of 30 is root 3 over 2. 10 root 3 over 2, that's 5 times 1.7, that's what, 8.5 meters per second squared. So that's my acceleration. And now it's just a matter of finding how long does it take to move that distance d. So I'm going to use my x equals 1/2 at squared kinematics equation. It starts from rest, so v naught I'll just leave off. And I put in my values here, 1/2 equals 1/2 of 8.5 times t squared. And then I solve for t. So that's 10 over 8.5. The root of that is equal to t. Let's go look at our values. Well, it's not 1, right? That would have to be the root of 10 over 10. It's not going to be 3. It's not going to be 2. So 184, well, is it going to be 2? Let's see. I must have a mistake here. I think the Answer is wrong. Give me just a second, I'll sort it out. I'm sorry, I sort of botched this up a little bit. Let me go back and readdress some of these things. Sort of several mistakes here, I apologize. All right, first of all, I was using H instead of D. So H here is 5 meters. And because this is a 30, 60, 90, D then, since this is 30 degrees, this is a 30, 60, 90 triangle. So this has to be 20, excuse me, not 20 meters, but 10 meters. So this is 10 meters. So the distance d is actually 10 meters, not 5 meters. And then also my acceleration, as I had written previously, is not g cosine theta, but it is g sine theta, which is going to be 10 times the sine of 30, which is 10 times a half, or 5 meters per second squared. And then it is largely the same. So I say x is 1/2 at squared. X is going to be 10 meters. That's equal to 1/2 of the acceleration, which is 5 meters per second squared, times t squared. So this t is going to be the square root of 4, which is 2 seconds. All right, so that's c. Sorry about that, but it's a good point. You need to read these carefully and make sure that you're aware of what variable is what. So here I was reading it very quickly, and I assumed that this distance was the distance that it was traveling, but obviously it's not. It's traveling down the distance of the inclined plane. All right, 186. 2 seconds is required for the mass to slide the distance d from a resting position. If the height h is now increased by a factor of 4 while holding theta at 30 degrees, how long does it take the mass to slide the new distance d from rest? Okay, well, the angle theta is still going to be 30 degrees. But whereas this was 5 meters, now it's going to be 20 meters. And so that'll make this 40 meters. Let's see how that affects our distance. Now it's going to slide that 40 meters. So x is going to be 1/2 at squared. It's not going to change our acceleration. So we'll just keep our same acceleration, since the acceleration is only dependent upon g and the angle theta. But since the angle theta is remaining the same, a is going to remain the same. So I'll keep using this 5 meters per second squared. So x is equal to 40 meters, 1/2 of 5 times t squared. That's 80 over 5. The square root of that is equal to t. What's 80 over 5? That's going to be 4 seconds. The square root of 16, or 4 seconds. So a is 186. If h is 5 meters, m is 2 kilograms, and d is 25 meters, and the mass starts from rest, how long does it take the mass to move the distance d? Okay, well, h is 5 meters, which is the same situation that we had up here. That makes this 10 meters. What else is different here? The mass is 2 kilograms. D is 25 meters. Okay, so the difference here is that our angle is no longer 30 degrees. So I have, let's see, this is 5 meters. And D is 25 meters, so this is 25 meters. I need to know what this angle is. The sine of an angle is 5 over 25. Let's see, that's not a simple sine. Let's see if we can approach it from a different way. Well, no, we can just take the sine of the theta as 5 over 25. And then our acceleration is going to be g sine of theta. So we don't really need to know the angle. We just need to know the sine of the angle. So that's going to be 10 times 5 over 25. That's 50 over 25, or 2 meters per second squared. So with this new angle, that gives us an opposite of 5 meters and a hypotenuse of 25 meters, will give us an acceleration of 2 meters per second squared. And then it's the same as before. X is 1/2 at squared. That's 1/2 of 2 times t squared is equal to 25. So t, these cancel. T is just the root of 25, or 5 seconds is 187. 189, if theta is 30 degrees, d is 10, and x is 10, how long after the mass reaches the bottom does it require to move the distance x? Okay, so let's see. We already know the velocity at the bottom, do we not? No, we don't, but we can find it fairly simply. We could do it in a couple of different ways. I'm going to use energy because energy, whenever you're dealing with things like this, is really nice. I say mgh, that's at the top, is equal to 1/2 mv squared at the bottom. So those masses cancel out. I have 10 times h, which if I look here, I have 30 degrees. It tells me that d is 10 meters. That's this distance. So this, since it's a 30, 60, 90, this has to be 5 meters because it's that 30, 60, 90. And this has to be half of the hypotenuse, opposite the 30-degree angle. All right, so 10 times 5 meters is equal to 1/2 of v squared. So v is equal to 10 meters per second. That's the velocity at the bottom of the inclined plane. There I've used the conservation of energy, which we haven't covered yet in these problems, but it's still a really useful thing for finding a final velocity, especially in an inclined plane like this. Okay, so now I want to know how long it takes to travel that distance of 10 meters. So it travels out here and travels a distance 10 meters. And I just want to know how long it takes. So it's pretty simple. There's no acceleration down there. So t is just d over v. That's 10 meters over 10 meters per second. Let's just check my units, make sure I've written this correctly. See, my meters cancel out, and I'm left with 1 second. So the answer for 189 is A. All right, 197. Object moving at 10 meters per second, make a circle with 2 meters radius. The object accelerates at what? But its centripetal acceleration is v squared over r. It's going to be 10 meters per second squared over a radius of 2 meters. That's 100 over 2, or 50 meters per second squared. Acceleration is a vector representing the rate of change of velocity. An object moving in a circle at constant speed is changing velocity constantly, all right, because the direction is changing. So it is accelerating, but it is changing its velocity, so A is not right. It has constant acceleration. That's not exactly true because the acceleration is also constantly changing direction. Changes speed, but not velocity. It says it's moving at constant speed, so that's not true. And so it has to be D. Changes velocity, but not speed. Remember, the speed is the magnitude of the velocity. The magnitude is not changing. Boy uses a string to swing a 1.5 kilogram stone around his head. If the string is 1.5 meters and compare a maximum tension of 1,600 newtons, what is the maximum speed at which the boy can swing the stone without breaking the string? So here I have this stone going around at a certain radius. The tension in the string is equal to the centripetal force. So it's going to be equal to mv squared over r. So that maximum tension is 1,600 newtons. It's going to equal 1.5 kilograms times v squared, which is what we're looking for, divided by the radius, which is 1.5 meters. Numbers are nice there. I get v is equal to 40 meters per second. That's the square root of 1,600. So A is 203. Man on a unicycle rides in a circular path shown below at constant speed. Which vector most closely represents the direction of the instantaneous net force on the unicycle due to the friction on the ground? So he's moving in a circular path in this direction. The centripetal force is always towards the center of the circle, and so the centripetal force is provided by the friction on the ground. This is like a car. It's the same as a car going around a banked curve or around a curve, and so C is the right answer. Remember that frictional force is the centripetal force. The Earth has a radius of approximately 6,400 kilometers, and an object could orbit the Earth just at its surface. How fast would it have to travel? It would have to travel in such a way that the centripetal acceleration was equal to the acceleration due to gravity. If the centripetal acceleration was less than the acceleration due to gravity, it would just fall to the ground eventually. If it was more, then it would shoot out into orbit. So it needs to be such that the centripetal acceleration, v squared over r, is equal to 10. And so v squared is equal to 10 times 6,400 kilometers. Or 64,000. The square root of that should be 80, right? 80 squared is let's see, that might be a mistake. Let me just double check this. Oh, yes, I see. I have made a mistake. Here, be careful with your units. This is 10 meters per second squared, which is going to be point zero. Let's say 10. I'm sorry, it's Friday afternoon. 1, 2. 0.01 kilometers per second squared. And then when I do 0.01 times 6,400, I get the square root of 64. All right, which is going to be 8. So be very careful with your units. This is in kilometers, but G, you have to do this in kilometers. It'd be nice to look at your units here too, so that you know which units to go to, because you might change the 6,400 kilometers into meters, but then you would have to do more work in order to do that. All right, so that's 207. 210, a 2 kilogram block rests on an inclined plane at 30 degrees. What is the static frictional force in the block? All right, this goes back to what we did before. I know that I have a force. This is the component of the weight, which is equal to FW sine of theta. Remember, this is the angle theta. Remember, our x and y components on the inclined plane are switched up because I'm measuring my angle from the y-axis, not the x-axis. So whereas the x component in projectile motion is given by the cosine, on an inclined plane it's given by the sine. So here my weight down the inclined plane is FW sine theta, and this has to equal the static frictional force if it's not moving. So Fs is equal to Fw sine theta. That is going to, Fs then is equal to 2 kilograms times 10 times the sine of 30, which is 20 times a half, which is 10. All right, 2 kilogram block rests on an inclined plane with an angle of 30 degrees. A steadily increasing force is applied to the block in a direction down the inclined plane until the block begins to move. If the block begins to move when the force reaches 7.3 newtons, what is the approximate coefficient of static friction between the block and the plane? Okay, we have a couple of things here. We can go ahead and use what we had before, where Fs has to equal Fw sine theta. Actually, no, let me redraw this because it's a little more complicated than that. We draw a diagram. To have this block, I have Fw sine theta. But then in addition to that, I have an additional force, F, because I'm pushing down on it. And this force, F, is equal to 7.3 newtons. Okay? And then I have Fs, which is up here. Now, I also need to know the normal force. If you go back to how we did inclined planes before, normal force is equal to Fw cosine of theta. Let's go ahead and put a value in here. The normal force then is going to be 20 times the cosine of 30, 20 times root 3 over 2. Which is 10 times root 3, or 17 newtons. So that's my normal force. Okay. So I'm going to say that Fs equals to, let me blow this up a little bit so we can see it better. Fs is equal to Fw sine theta plus, I don't know where that went. Well, shoot. Fw sine, sorry, I don't know what's going on. Fw sine of theta plus 7.3. That comes from this. Fs have to equal the sum of those forces. And I know that my static friction is equal to mu s times my normal force, which I found to be 17 newtons. Now, let's see, I can put in some additional numbers. I know that this is 20 times the sine of 30, which is 10 plus 17.3 equals mu s times 17. So that's 27 over 17, which should be 0.6. So here we get 27 equals mu s times 17. And so mu s then is 27 over 17. The only one it could be is B. That's the right answer for 212. Following experiment takes place on the moon. A 2 kilogram block rests on a flat board. One end of the board is slowly lifted until the block begins to slide. If the block begins to slide when the board is angled 30 degrees of horizontal, what is the coefficient of static friction between the block and the board? Okay, well, we've already seen this a bit. Remember I have this block right here. This is 30 degrees. I have these forces. This is my static frictional force. This is my weight times the sine of 30 degrees. And I know that the maximum static frictional force is equal to mu times the normal force. And my normal force is mu times the weight times the cosine of theta. So this is my normal force, Fw cosine theta. It has to equal to the y component of the weight. Okay, so I'm looking for the coefficient of static friction between the block and the board. I also know that Fw, that my static friction has to equal Fw sine theta, so I'm going to put that in here, Fw sine theta. Notice that my Fw's cancel out, and I'm left with mu is equal to the sine of theta over the cosine of theta, and that's equal to the tangent of theta, or the tangent of 30 degrees. And the tangent of 30 degrees is 1 over root 3, or 1 over 1.7, and 1 over 1.7 is 0.6. This was an expression, actually, that we had in our section on friction, was that mu is equal to the tangent of the angle theta. I didn't think it was very useful, but I see it's there. So it might be something that you want to just put on your memory page that you want to memorize. Block is at rest on a plane incline at an angle of theta. Which of the following is a true statement? This is number 218. Well, if it's on an incline and playing angle theta, if it's at rest, that means that it's not accelerating, so there can be no net force acting upon it. All right, almost done here, I think. Okay, when a car moves under its own power at constant velocity, the frictional force between the road and the tires that propel the car is which of these? Well, if it's under constant velocity, first of all, the frictional force between the tires and the road is a static frictional force. And so that gets rid of C and D for 225. And the frictional force if I imagine my tire here, my car is moving in this direction, and so the tire is against the road. I'm looking for the frictional force between the road and the tires. That frictional force is going to be in this direction. Is that right? Yeah. And so it's going to be A is the right answer. A car moving at 20 meters per second brakes and slides to a stop. The coefficient of kinetic friction between the pavement and the tires of the car is 0.1. How far does the car slide? All right, several ways you could do this. You could find the kinetic frictional force. No, you couldn't do it that way. The easiest way here is to use the work energy theorem. And that is to say that the frictional force, this is actually going to be kinetic because they're sliding, times d, that's the work done by the frictional force, has to equal the energy, the kinetic energy of the car. All right, Fk is equal to mu k times the normal force, which is mg in this case, is equal to 1/2 mv squared. Our masses cancel, which is good because we don't know the mass, and we're looking for d, so d equals 1/2 of my initial velocity, which is 20 meters per second squared, divided by 0.1 times 10. So that's half of 400, or 200, divided by 1, so it should be 200 meters. Just see. Assuming that a vehicle slides to a stop without brake or tire fail, which of the following is not true? All right. A heavy truck will require more room to stop than an economy car. That is not true. In fact, we've seen up here that the masses cancel out, so it doesn't matter about the mass. Now, given it does require a greater force to stop the truck, but the truck also has more mass, so a greater normal force, and hence a greater frictional force. So that one is not true. The number of wheels on a vehicle does not change the time needed to stop it. That is true. More contact area with the road gives you greater friction. Acceleration is constant until the vehicle stops. That is true. If it's sliding to a stop, that kinetic friction is going to always be the same, mostly. A greater kinetic coefficient of friction means a shorter stopping time. That's true. If you have a greater kinetic coefficient of friction, that means you have a greater frictional force, so it's going to stop more quickly. All right, 230. 3 blocks of the same shape and made from the same material, masses 1, 2, and 3 kilograms, placed on a board. Board is slowly lifted on one end. Which block will slide the fastest? Well, the answer here is D. I'll show you why. Do it over here. So if I have this block over here, this is my angle theta, and I want to know how fast will it slide. That is, which is going to have the greater net force. Net force is going to be my frictional force in this direction, and my component of the weight, that's going to be Fw sine of the angle theta. And so the net force acting on this, which will describe how quickly it accelerates, will equal F minus Fw sine theta. That's going to be my net force. All right, F is equal to mu times my normal force, which is Fw cosine of theta. That's my normal force, minus Fw sine of theta. And this is all going to equal the mass of the block times the acceleration. Now notice here that I have mu mg cosine theta minus mg sine theta equals ma. The masses all cancel out here, and so it has no dependence on mass, is the point here. So all the blocks would slide with the same speed because they'll all have the same acceleration. Professional strongman ties a rope to a building and pulls as hard as he can on the rope. 2 other strongmen take either end of rope B and pull in opposite direction as hard as they can. If all strongmen possess equal strength, how do the tensions in the ropes compare? Okay, so we had a question similar to this. Here's my building and my rope. I have a guy that's pulling it, say, with 100 newtons or whatever. All right, and then over here I have 2 guys pulling it. A rope, they both pull with 100 newtons. The ropes are both going to have the same force acting in them, 100 newtons. Now, if imagine this, imagine that you just replace this guy with a building. That's the same situation, because when this guy pulls with 100 newtons, the building pulls back with 100 newtons. A woman dangles a mass 50 kilograms from the end of a rope. She stands on a frictionless surface and hangs the mass over a cliff where the pulley is shown. The tension in the rope would be what? All right, let's just draw our forces. We have the weight here. This weight, I'm going to go ahead and put in some numbers here. This weight is 500 newtons. This is my tension. This mass is 50 kilograms. And then I have a tension here. Okay? There are no forces opposing this because there's no friction. So I can write over here that Ft minus mg equals ma. I'm just going to write them as variables right now. Over here I can write that Ft equals ma. Now in this case the mass of the block equals the mass of the woman, so I'm just not going to draw any distinctions. I'll just leave it as m. All right, now I'm looking for, gosh, what am I looking for? The tension. So I want to find the tension. So look, I have two expressions here that are equal to ma. So I'm just going to set them equal. I'm going to say ma equals ma. That is that Ft minus mg equals Ft. And then I can solve for Ft. Ft then equals mg over 2. That is 500 newtons over 2. That's the weight of this divided by 2, or 250 newtons. All right. What is the minimum force required to lift this mass? I have this pulley system. There are lots of sample problems, or lots of problems I've seen on the practice test for this. Basic tension problem, I apply a certain force here, and that tension is applied here and here. So I have twice the tension holding up this. This is 60 newtons. That means that each of these has to apply 30 newtons. So the minimum force required is 30 newtons. What is the minimum force required to lift this mass? Okay, well the answer here is going to be the same. It doesn't matter if you apply it at an angle. If you get 30 newtons here and 30 newtons here, you're going to lift that 60 Newton block. So 466 is 30 newtons. And a man dangles a 10 kilogram mass on the end of a rope. He sits on an elevator while holding the rope. We had a problem like this in 101. Have 10 kilogram mass. It's accelerating downward. So A is equal to -3 meters per second squared. And I just say the sum of the forces equals ma. I have the tension in this direction, the weight in this direction, so Ft minus Fw equals ma. I'm looking for the tension. That's going to be 100 newtons, that's the weight of the block, plus 10 kilograms times -3 meters per second squared, because it's accelerating downwards, so that's equal to 70 newtons. What minimum force is required to lift this mass? Okay, well here, notice I have 1, 2, 3, 4 vectors pulling up a 60 Newton block. So each of these vectors has to be 15 newtons, and so this only needs to be 15 newtons, giving me a significant mechanical advantage. All right, well that's it. We'll see some of these other topics that come up in the later questions, but that's a good sampling of Chapter 3.